One of the things that we want to summarize, this is still working in section 2.3, before we go on to the next problem, is something we observe in the solution of example 5. When we solved the initial value problem, we got the solution y equals x minus 1 plus 5e to the negative x. That was the particular solution to our initial value problem. We also saw that if you look at the family of solution curves we had to the general differential equation, they were of the form y equals x minus 1 plus c e to the negative x. And the value of the constant that solved our initial value problem was the constant 5. What I've done here is kind of picked a couple different values of c, and we want to kind of graph a couple of these solution curves together to kind of see what the graphs look like. And one of the things that we notice pretty quickly is that the graphs are all going to be different functions, but as x approaches to positive infinity, these curves are all quite rapidly approaching what looks to be a straight line. And we could think about that if it's a particular member of the family that would actually have the c value equal to 0. So if you look at the line y equals x minus 1, that curve, it looks like, is what all of the solutions are approaching when x approaches infinity. And one of the reasons for this let me get my snipping tool up here, is because the following. With this family of functions, if we have y equals x minus 1 plus c e to the negative x, the c e to the negative x, this is the same thing as c divided by positive x. And so what happens is this term, as x approaches infinity, the denominator is going to get larger and larger and larger, whereas the numerator is going to stay some fixed value, which means that this thing is going to go to 0 as x goes towards infinity. So what we see is that as x approaches infinity, our function is going to start to begin to look like this piece goes to 0. It's going to be kind of looking like the function x minus 1. We refer to this term, the c e to the negative x, there's a name for this, it's what's called a transient term. A transient term is any term that goes to 0 as the independent variable goes to infinity. Okay? And we will see some of these in solutions, and they have a major importance sometimes when it comes to applied problems. The next example we're going to look at, this is example 6. Still working with a linear first-order differential equation. But what makes this one a little bit different is that the function f of x, it's in standard form, by the way, so that part's already taken care of for us. But if we look at f of x is actually defined piecewise. F of x is going to be equal to the function 1 when x is between 0 and 1 inclusive, and it'll be equal to 0 when x is greater than 1. Okay. So essentially what we have, if I kind of write this out, we're going to have dy dx plus y, and this is going to be equal to 1, and that will be on 0 less than or equal to x less than or equal to 1. And it's going to look like dy dx if I can get my whiteboard back. There we go. If dy dx plus y equals to 0, and this is going to be on x greater than 1. What's nice is that these functions both have the same p of x value, so in either case, p of x is just 1, so we should be able to find our integrating factor. The integrating factor is e to the integral of p of x dx. This is equal to e to the integral of 1 dx, and the antiderivative of 1 is just going to be x. So our integrating factor for these is going to be e to the x. So we're simply going to go ahead and multiply every single term on both sides of our differential equation by e to the x. And now we can go ahead and solve these. We know that this expresses the left-hand side as an exact derivative. It's the integrating factor times the solution function y. It's going to be equal to e to the x. Similarly for this one, we're going to have e to the xy, in this case simply equals to 0. And now we integrate both sides to solve for y. We're going to take the antiderivative with respect to x. For this one here, what we would get, the derivative and the integral cancel, so we get e to the xy is going to be equal to e to the x plus c. And then we can solve this equation for y by simply dividing both sides by e to the x. So we would get y equals, these cancel and give us 1 plus, and I'll just write it as c e to the negative x. Okay. And this part of the solution, keep in mind, is for 0 less than or equal to x less than or equal to 1. Now, this is an initial value problem. They say that the value of the function at 0 should be equal to 0, which means that we can solve for this particular constant of integration, and maybe I'm going to call it c1, because you'll see in a minute we'll have a different constant of integration when we solve the second portion of this function. So if I plug in 0 for x, we should get 0 for y. So it's going to be 0 equals 1 plus c e to the negative 0. That's going to be 0 equals 1 plus c. So c should be equal to negative 1. So for this one, c is going to be negative 1. So here's what we have. We have y equals 1 minus e to the negative x. And this portion is valid on 0 less than or equal to x less than or equal to 1. For this piece over here, let's go ahead and finish that off. Again, the integral and the derivative cancel. We get e to the x is going to be equal to, this is going to be some constant. Let me just call it c2. We can divide both sides by e to the x, and we get that y is going to be equal to c2 divided by e to the x, or you could simply call it c2 e to the negative x. And this part of the solution is valid for x greater than 1. So we've solved it out. This is what we have. We weren't given a second initial condition to solve for c2, but y is equal to 1 minus e to the negative x, and this is on 0 less than or equal to x less than or equal to 1, and right now it's going to be c2 e to the negative x on x greater than 1. One of the things that we could do at the very minimum is that it would be nice to see if there exists a c2 such that we can make our piecewise defined function solution continuous at x equals to 1, because that's kind of the split point of this piecewise defined function. So let's see if at least we can pick a efficient value for c2 in order to make that occur. So this is a good old blast from the past. We're going to revisit continuity of a function at a point. So remember, this part function here, this is valid for x is greater than 1. So if we want this function to be continuous at x equals to 1, we're going to need the following thing to happen. We're going to need the limit as x approaches 1 from the right. That's going to be this portion of the curve. This should be equal to the value of the function. at that point. It should be equal to y of 0. Excuse me, y of 1. Again, by definition, if you remember from Calc 1, the limit as x approaches to c of f of x, if this is equal to f of c, then this is the definition of f being continuous at x equals to c. Well, this limit on the left-hand side can be found by evaluation. Everywhere we see an x, we can put positive 1. For the value of the function at 1, that's going to come from the first piece. That would be 1 minus e to the negative first power. And now we just kind of need to go ahead and solve for this. For some of us, it might be helpful if you wanted to. You could think of this as being c2 divided by e equals 1 minus 1 over e. And then simply multiply both sides of the equation by e. We would get that the value for c2 should be equal to e minus 1. So that enables us to do a little bit better. Instead of just having a generic second constant hanging out there, we're actually able to find a value of c2 that would give our solution a continuity on the whole interval from 0 to positive infinity. Because it was continuous in between, and now it's also continuous at 1. So this guy was what? E minus 1 is the constant c2, e to the negative x. Now that's for x greater than 1.